This is Chapter 3, Valence and Ionic Compounds, Part 3. So we're going to use some examples of ionic compounds, and we're going to illustrate all the different principles that you need to know in terms of ionic compounds. How to write the formula, how to write the name, why they combine the way they combine, all that kind of stuff. So remember, if it's ionic, the whole point is that the elements, one of the elements is going to give electrons, the other one's going to take electrons. And so that turns them into ions because they've either given up electrons or taken electrons. And so if they give up electrons, they are cations, and cations are positive. And anions are ones that have accepted electrons, and they are negative. But either way, they're doing it to complete that full valence shell. That's what we call the octet, right? Sometimes it's 8, sometimes it's 2. And so when we look at this, the interaction of the two ions, so the interaction of a positive to a negative and the negative to the positive, that interaction between the two, that is the ionic bond. And it's very strong, and it holds these things together. And so what we're going to do is we're going to look at some examples of some different ionic compounds. And what I want you to do is, on your paper, we're going to add some stuff to it. So we're supposed to be examining our data set here. And we're supposed to notice that none of the compounds have a net charge, that the positive charges and the negative charges all add up to 0. But you got to kind of work that out for yourself. So I want you to add this little table to your sheet, and I'm going to do 2 with you. And so we're going to look at this first one, NaI. And so NaI is sodium iodide. And so when we do this, if you look at your periodic table, you should be able to find any of the elements and identify what charge they turn into. So if we look first at sodium, sodium symbol is Na. Na is going to be in, and I guess I could show you a periodic table. Let's see. Show you a periodic table, and this is what you should be doing, right? Okay. So let me kind of erase what's going on over here. Na is sodium. It is right here in group 1A. So it has 1 valence electron. It's going to lose its 1 valence electron and going to end up with a charge of +1. So we're going to put Na plus. Now, I also want you to write in this little box how many of these sodium ions I have. And if there's nothing here, right there as the subscript, whoa, right here, it's a 1. So Na, so I have 1 Na plus ion. Okay, what is my anion? My anion is iodine, but it's become an ion, so it's iodide. So if we come over here, here's iodine, and iodine turns into iodide. It's in group 7A, so it's 7 valence electrons. It's going to gain 1 and become a negative ion, an anion. And so you're always going to see that the cation's first, the anion second. So if we look in the formula, our anion has only 1 of it, 1 atom of it in the ratio. Okay, so I have 1 sodium ion and I have 1 iodine ion. So what I want you to do is I want you to figure out the net charge. And so the way that you do this is you take the number of each. So I have 1 sodium ion, so that's my 1, and I'm going to multiply it by the charge. The charge is a +1. And I'm going to add the positive charges to the negative charges. And so for the anions, I have 1 atom that is a -1. So a +1 and a -1 give me a net charge of 0. That's how I know my formula is correct. So I want you to do that for all of them. But when you get down here, you're going to see that there are some weirdo ones, right? That have Roman numerals. These are the ones that that are transition metals, and these transition metals are able to have multiple charges. So we have to give their charge when we give the name. So we say copper 2 bromide. So let's do that. If it's copper 2 bromide, what does this Roman numeral 2 mean? This Roman numeral 2 means you're always going to have the cation first. So this is always going to be positive. And then you just have to know, how positive is it? Is it positive 2, positive 3, positive 4? Well, the Roman numeral 2 tells you it's a +2. So the copper has a charge of +2. All right, so I'm going to come over here and I'm in the same line and I'm going to say my copper, my Cu, has a +2. So how many of those +2 coppers do I have? Well, in the formula, there's nothing there. So that means I have one of them. Bromine, on the other hand, I have 2. And I know bromine is in 7A, so it's a halogen, so it also has a charge of -1. So I'm just going to put a negative right there. So now I'm going to do my same thing, where I say the number of atoms times the charge, number of ions really, times the charge of the ion, plus the number, which is 2, and the charge of the ion, which is -1. So that ends up being a +2 and a -2. So +2 minus 2 give me a net charge of 0. I want you to pause the video at this point, and I want you to complete the rest of the table. Okay? So I'm assuming you have paused it, you have completed the table. So what I'm going to do is I'm going to erase all of this, and then I'm going to put in a completed table because I copied and pasted one that I already did. Okay, so I'm going to just kind of get rid of all of this junk and then paste in my good table that is completed. See if this works. No. Uh-oh, I'm going to have to pause it and get back to y'all. Hold on. Okay, so we now have our completed table. And so you can pause the video at this point and you can check all of your answers. But what you should see is that the net charge on every single one of these ionic compounds is 0. And that is the definition of an ionic bond. So now we're going to go down and work on some of these questions. In naming ionic compounds, what goes first in the name? The metal or the nonmetal, the anion or the cation. So if we look at all of these, right? Everything, let's see if I can kind of erase some of this stuff. Everything that comes first, sodium, potassium, calcium, magnesium, copper, iron, aluminum, they are all metals. And what do metals do? Metals have less than 4 valence electrons, so they're going to lose those valence electrons. They lose negatively charged particles, and they become positive, which is a cation. So same thing in the formula, our cations go first. Remember, cats are so cute, and you're always going to let them go first. So number 2, how are anions and cations the same? How are they different? Well, so let's talk about how they're the same first. And always remember, try to answer these without watching the answer, me do the answer. So do it yourself, then watch me. So both are charged, right? So that's a true statement. Both have a change. So both have a change in the number of valence electrons as compared to their neutral atoms, right? So, or you could say both are charged because, you could actually say it that way. That's kind of a better way. Both are charged due to a change in the number of valence electrons from the neutral atom. Right? You had a neutral atom, it changed its number of valence electrons and therefore became charged. So how are they different? So let's talk about anions. What do anions do? Anions are going to gain electrons and become what charge? And become negative. Anions are metals or nonmetals? Nonmetals, right? Okay, then cations. Cations, and remember, anions are negative. Cations are positive. They're positive. It's cations, right? These are going to lose valence electrons and become positive. And these are metals. Metals do this, okay? All right, in potassium sulfide, so if we come back up and we look for potassium sulfide, there's just so much going on there. Okay, so here, potassium sulfide, K2S. So K2S, that's our formula. What's the charge on the potassium ion? What's the charge on the sodium ion? So let's do this. So if we have K is in group 1, right? That means it has 1 valence electron. It's going to lose its 1 valence electron. It's going to end up with a charge of +1. Sulfur. This one is in group 6A. It has 6 valence electrons. It's going to gain 2 valence electrons for a charge of -2. Okay, so now that we know the charges, I'm going to show you 2 different ways to get to this formula. So the first way is kind of the long way, but that's okay. It's going to make sense. So I'm going to start with my potassium. How many valence electrons did we say it had? It has 1. All right, and then we're going to have a sulfur atom. And a sulfur atom has how many? Should have 6. So remember, when we do these electron dot diagrams, we put our electrons singly, 1, 2, 3, 4, and then we double them up. So then we'll say 5, 6. It doesn't matter how you do it. It does not matter at all. So neither one of these atoms are happy. They want to turn into ions, and we know potassium wants to give up an electron, and we know sulfur needs some electrons. So what would happen if potassium said, hey, sulfur, would you like my electron? And gives this 1 electron to sulfur. So now potassium no longer has it and becomes an ion, right? So potassium's happy. Sulfur's not quite happy yet. It only has, count these valence electrons, it has 2, 4, 6, 7 valence electrons. That's not good. It's not going to cut it. So we need another atom of potassium that has 1 valence electron. It's going to give up its 1 valence electron to sulfur. Say, here you go, sulfur. Now you can have a complete octet, and so do I, because I lost that outer valence shell electron. So I'm going to need 2 potassium atoms for every 1 sulfur atom. And so that's why I get the formula K2S, because I needed 2. So that's a long way around. You could take the shortcut. So I know I have a potassium atom that has a charge of +1. I know I have a sulfur that is -2, 2-. So in order to complete my formula, all I have to do is do what's called the crisscross method. So you take the charge on one, that becomes the number of atoms on the other. But what does plus mean? Plus means +1. So whenever you go from a charge to number of atoms, you drop that positive or negative sign and you just leave the number. Same thing here. I'm going to take the 2 negative, drop the sign, and say, okay, now that's 2 atoms of potassium. And this works every time You might have to reduce, but in this case, we didn't have to. And we get the same answer, K2S, K2S, K2S. And so that's two different ways to do it. It's a whole lot quicker doing the crisscross, but I'll show you a few special cases, right? Okay, so why does the formula for potassium sulfide have 2 potassium ions and 1 sulfide ion? Well, let's talk about this. So what does sulfur need? Sulfur needs to gain 2 valence electrons, right? To have its complete octet, to have complete octet. So each potassium atom only has 1. So each potassium atom only has 1 valence electron to give up to complete its octet. Its octet. So what do you need? So you need 2 potassium atoms to each give up their 1 valence electron to 1 atom of sulfur. Now both are happy. Okay. All right, some of the names of ionic compounds have Roman numerals after the metals and others do not. Consider their position on the periodic table. What's the difference about metals with Roman numerals versus metals that do not have Roman numerals? So if we come up here and we see these, copper, iron, what do they have in common? So if we look on the periodic table, we see that we have copper. If I could find my copper. You ever have those days? Whoa! Here's our copper. And we have iron, copper and iron. Where are these located on the periodic table? They're located in the transition elements, and they're really transition metals, right? And so these transition metals, we said, can have multiple charges. So any metals, any transition metals, so metals with Roman numerals are transition metals. Okay, so metals without, let's try to do another statement, metals without Roman numerals are main group metals, okay? So that you know the difference. Okay, now this is gonna get a little tricky. The charge on one of the irons, let's zoom out a little bit, and let's kind of move this up. This is kind of terrible. I'm gonna need all the space I can get. All right, so the charge on one iron in Fe2O3 is what? Okay, how do we figure that out? What we're gonna do is we're gonna do the reverse crossover. I'm gonna start with the formula, Fe2O3. Fe is a transition metal. It can have multiple charges. Oxygen, on the other hand, can only have 1 charge. So I'm going to do my reverse crossover. I'm going to say what was the number of atoms is now going to become the charge. It's 2. If oxygen is a nonmetal, oxygen must carry a negative charge. So that oxygen must be 2 negative. If We check the periodic table and we know where oxygen is on the periodic table. 6A, it has 6 valence electrons. It's going to gain 2, so therefore charge of -2. That's correct. Now I'm going to take my subscript on the oxygen, turn it into the charge for the iron. The iron is going to become a 3+. So the charge on one iron in Fe2O3 is +3. And so this is just the reverse crossover, right? And so we know we have Fe 3+ and we have O2-, right? It's really, 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 really important to check the periodic table for the charge on main group elements. I'm going to show you why in a minute. Group elements. Okay, so why is that super important? Well, let's try the next one. Imagine that, right? Okay, so we have FeO. What's the charge on the iron on FeO? It's still iron, but how do I know the charge? Well, I'm going to do the reverse crossover. But here's my problem, right? If there's nothing there, what can I assume is there? A 1, okay? So now I'm going to take my 1 and I'm going to do the crisscross. And I'm going to say, okay, if it's a 1 there, it's a 1 here. And then oxygen has to be negative because it's a nonmetal. And then I'm going to do the reverse. I'm going to take the number of oxygen atoms and make it the charge on iron. And I look at that and I go, no way. Oxygen is a main group nonmetal. It must have a charge of -2. Must, always. It's main group. So I'm going to have to change, but I can't just change my oxygen. If I change my oxygen, I have to change my iron. So is there a number that I can multiply both of these numbers by in order to make oxygen 2, -2? And that number is 2. So if I do 2 times +2, what do I get? I get Fe, that is 2 times 2 is 4, and I keep the positive, +4. Then I'm going to do 2 times -1 for oxygen. Oxygen, 2 times -1 is -2, or 2 negative. Yeah, I forgot how to do that. 4 positive, right? So what is the charge on one iron ion in FeO? It's going to be 4+. How did no? I did that wrong. I did that wrong, y'all. I crisscrossed because that's crazy. Come on, Dr. B. Okay, so that's 1 because this was a 1. This has to be a 1. So how do I make that? I make that a 2. My brain was skipping ahead. So now what is my iron? 2 times 1, +1, is +2. It's looking at it going, that's not right. So don't do that. Okay, so now what is the charge on one iron atom? That charge is +2. Okay. All right, so based on your answer to question 5, what do the Roman numerals mean? Well, if we looked up above, we had, right, iron 3 oxide, and then we had iron 2 oxide. So if we looked up here, we had Fe2O3 is iron 3 oxide. FeO is iron 2 oxide. So what does that 3 mean? That 3 means that that's the charge. So the Roman numeral is the charge on the transition metal. Okay. Based on your answer to question 4, when is the Roman numeral used in the name of ionic compound? Only on transition metals. How does the name of the nonmetal part of the compound differ from that of the original element? So let's come back up and kind of look at these. So nonmetal, if I had iodine, now I have iodide. I had sulfur, now I have sulfide. I had fluorine, fluoride. Nitrogen, nitride. All I'm doing is adding an IDE to the end of my nonmetal or my anion. So how does the name differ? So you drop the last few letters of the element name. Element name and add IDE. And that gives me my name of my anion. Okay. So everything we've talked about so far has just been one ion combining with another ion. But you can have polyatomic ions where poly meaning many, atomic meaning atoms. So many atoms together are charged. That's what an ion is, are charged. Okay, so it's a group of atoms that act like an anion or a cation. And so it's another way to make an ionic compound. And you'll have these on your best friend. You have more than this on your best friend. But you have to be able to go from a formula to a name and go from a name to a formula. So it's much easier to go from a formula to a name. So for ionic, all you do is name the cation. So the cation is potassium. It's the potassium ion, but when we're naming it, we don't put that. And then Cl is chlorine, but we're going to drop those last few letters and make it chloride. So it should be potassium chloride. All right, we have the name for the next one, sodium sulfate, but we don't have the formula. So what I'm going to do is I'm going to say sodium is Na. I go to the periodic table and I look and I say, okay, sodium's a +1. Sulfate, ooh, that's weird. Why would something end in ATE? If it ends in ATE or it ends in ITE, there are none on here, but ITE is another example of the ending for a polyatomic ion. We know that it's polyatomic. There are a couple of exceptions, like ammonium doesn't end in ITE or ATE. Hydroxide, unfortunately, ends in IDE, but the majority are ITE or ATE endings. So I would see that ATE on sulfate and go, oh, I got to go to my polyatomic ion table. And sulfate is sodium atom and 4 oxygen atoms. And this whole group carries a charge of -2. So now I need to make a formula. So I'm going to do that reverse crossover. I'm going to say I have an Na plus and an SO4 2-. So I want you to kind of think about all the time of polyatomic ions together. We're going to put it in parentheses. You can't touch it. You cannot change anything that is within those parentheses, okay? So I'm going to take my charge from one atom and turn it into the number of polyatomic ions I have. So that's a 1, but I drop the charge. Same thing, I take my charge, turn it into number of atoms, so that's a 2. And so once you rewrite it, then you can decide if you need the parentheses or not. So Na2, SO4, 1. Well, if there's a 1, we just don't write it. So it would be Na2, and if we don't have a 1, then we don't really need a parenthesis, and we just write SO4. So that's what we would put over here, Na2, SO4. All right, the next one. We have iron. And then, we have to think about the charge on this. So I'm not sure what the charge is on iron, but I know that I have an OH with a 3 on the outside. So what we're going to do is we're going to do the reverse crossover and see if it works. So we get a +3, And really there's a 1 right here. So I'm going to do the reverse. It's going to be a 1 negative. Well, what is OH? OH minus is hydroxide. And so it does carry a charge of -1. So the iron must be iron 3. And then all I have to do is name my polyatomic ion hydroxide. Okay. Let's see. The next one, anytime that you have more than 2 elements in your formula, you're going to have a polyatomic ion. So here in FeOH, I had iron, that's 1, oxygen, that's 1, hydrogen, that's 1. So it's 3 different elements. So therefore, I know I'm going to have a polyatomic. In the next one, NaHCO3, I definitely have more than 2 elements. So I know I'm going to have a polyatomic. And so I kind of start to look for that. And I go, okay, here's a polyatomic that matches. Okay, so I just want to write the name for this. So the Na is sodium. It's a main group, so I don't need any parentheses and Roman numerals, none of that. And then I look up here and I say, okay, HCO3 is bicarbonate. So it's sodium bicarbonate. And that's it. All right, the next one, oh, we got to go from a name to a formula. So I'm going to say ammonium. What is ammonium? I come up here to the top and I find ammonium. Ammonium is NH4 plus. So this whole polyatomic ion carries that charge of +1. And then nitrate is right here. So this is NO3, and this whole thing carries a charge of -1. And so I'm just kind of putting them on the outside of the parenthesis just so that you can see that that's what happens. So I do my reverse crossover and I put a 1 and I put a 1. Well, do I need the 1s? No, I don't need the 1s. So do I need the parentheses? No. So I can just rewrite this as NH4 NO3. Pretty nice. All right, the next one, silver 1. Well, that's really easy. I can put my symbol and then it's a +1 because I see the Roman numeral and that's a 1. Then I go up and acetate. I come up here and I find acetate. Acetate is C2H3. O2. Okay, and it carries a charge of -1. Should have done this in a different color, but that's for that one. Okay, so now I'm going to do that reverse crossover. I'm going to take the charge on here and I'm going to put it outside my polyatomic. Charge on here, put that here. Well, it's just 1s. So all I have to do is write Ag, a 1 you don't write, C2H3O2, and that's it. Okay, calcium. So, oh, here I have more than 1. I have more than 2 elements, right? I actually have 4 elements here. So I know I have a polyatomic. So it's not going to be probably my metal. So I want to go look for HPO4. So I come up here and I look and I find HPO4, that's hydrogen phosphate. So I'm going to have to name my metal. So this is calcium, hydrogen, phosphate. Much easier going from the formula to the name than in the reverse, but that's okay. All right, mercury 2 chloride. Mercury symbol is Hg, and it has a 2 plus. Chloride is Cl, and it has a -1. Let's kind of come out here. We'll do it where we have a little bit more room. So we have Hg 2 plus, and we have Cl minus. So what we're going to do is our crossover. Take our charge, make it the number of atoms, but drop the sign. So Hg1, I don't have to write the 1, I just write Hg, and then Cl2. Okay, this very last one, aluminum carbonate. So aluminum is Al, main group, 3 plus. Carbonate, I come up here and I'm going to find carbonate, and carbonate is CO3 2 minus. Okay, now I got to be really careful here. So I think I'm gonna go ahead and give myself a little bit more room and put it down here. Al3 plus, CO3 2 minus. And I'm going to go ahead and put my polyatomic in brackets just because I want to keep it together. I want to make sure I know what I can change and what I can't change. I can't change the polyatomic ion. So I'm going to take my charge on my aluminum. That's going to become the number of my polyatomic ions that I need, and vice versa. Okay, so now all I have to do is recopy this. This is Al2, open parentheses, CO3, 3. So I need to keep those parentheses for this example. Everything else we've been able to drop them, but here we need to keep them. So be very, very careful that you put parentheses exactly where they need to go. So now I want you to pause and I want you to fill in this table now that we've gone through that. So I'm going to go ahead and pause it and you go ahead and try it. So you should have paused it. Here are our answers for the formula and the compound name. So just double check and make sure you have that correct. The only one that's a little bit tricky is right here, this one right here, where we're combining zinc and fluorine. Zinc looks like a transition metal, and you're 100% right, it is. So if we pull up our our periodic table, right, we see that right here, zinc is a transition metal, but it's an exception. There are 2 exceptions to this rule. They are zinc and silver. So the way that I remember this, zinc and silver have set charges. Even though they are transition metals, these are 2 transition metals whose charges never change. Aluminum is in group 3, so it's going to become a +3. Go on the diagonal, zinc is a +2, silver is a +1. So it goes 3, 2, 1. So that's how you remember that. So even though zinc is a transition metal, it does not have Roman numerals. So just remember that. All right. So lactated ringers and 5% dextrose injection. So this is something that you'll find in an IV. So these are electrolytes that if somebody's dehydrated and they need fluids, that we give them in an IV. And so a lot of times you're going to see lactated ringers solution in IVs. So the highlighted substances, right? Let's what are we supposed to do here? We're supposed to provide the formula for the names. Okay, so the names that we have are sodium chloride. We have potassium chloride, bunch of chlorides here. Calcium chloride. So all I did was pull out those that were highlighted yellow. So in order to do this, all I have to do is find out what is my ion symbol for each of them. Na plus, Cl minus. K plus, Cl minus. Ca2 plus, Cl minus. And so now I'm just going to do my crisscross, where you take the charge on one, make it the number, charge, make it the number. So that gives me NaCl, because I don't write the ones. I get KCl. Now, be careful here, because when you get to the last one, that's going to be a 2, that's a 1. So you end up getting CaCl2. The last one, give the formula. Okay, lithium. Lithium's going to be a +1, and carbonate. Well, let's come down here. I don't really have enough room. Okay, lithium is Li plus. Carbonate is CO3, 2 minus. And remember, this should kind of be in a parenthesis, okay? And then we'll decide if we need to keep them. B, we have potassium, which is K plus. And we have permanganate, which is MnO4 minus. I don't know if that one's on your best friend. But I'll only give you on a test ones that are on your best friend. And then C, we have sodium iodide, Na plus, I minus. And you have to know IDE, you're not going to the polyatomic ion table, you're just going to the periodic table. Okay, so now we're going to do our crossovers, right? That's a 1, that's a 2, that's a plus, it's going to be a 1, that's going to be a 1, and a 1. Okay, so now all I have to do is rewrite them. So I have Li2, and then since CO3, since I only have a 1, I don't need the parentheses, so I'm going to just say Li2CO3. Here I have K1, but I'm not going to write the 1, and then the MnO4, I only have one of them, so I don't need the parentheses, MnO4. And then I have NaI. And that's it. All right, I hope this helps.